Hi everyone! This video looks at a weak acid titrated with a strong base. Here we will focus on the initial pH when 0 mils of titrant have been added. Because the titrant is at 0 mils and no reaction has occurred yet between the acid and the titrant, we do not need a millimole table. We're just calculating the initial pH of the weak acid by itself. To calculate the pH of a weak acid, we must set up a reaction table. When the units are molarity, I call these mice tables. This sample mice table shows the general layout. Notice that the chemical equation at the top is for the dissociation of a weak acid having the generic formula HA. The rows are set up as I for initial, C for change, and E for equilibrium. We will know our initial HA molarity because it's given in the problem, but the products, H plus and A minus, will be 0. The change that occurs with this equilibrium is that some of the HA is lost because it dissociates, and a stoichiometric amount of H plus and A minus will be gained. The terms here are all 1x because the balancing coefficients for the chemical equation are all 1. For the E row, we do the math for what is happening with the change. What you'll see is that when we solve the problem, we will initially assume that it is okay to ignore the change in X as related to the HA. Then we'll check that assumption later. We cannot ignore the X's shown in the E row for H plus and A minus because they are standalone X's. To calculate the pH, we'll set up our mice table like we just talked about. Then we'll solve for X, which is H plus, by ignoring the change in X. And we'll go back to make sure that our assumption is valid. Once we have H plus, then we can calculate the pH directly by taking the negative log of that number. In our example, we see that we do have 0 mils of titrant, which tells us that this is initial pH. So the information we need comes from here, which is the molarity of our weak acid. So the first thing we do is set up a mice table for weak acid equilibrium. And I'm going to use the generic notations. So we have HA dissociating to form H plus plus A minus. This is a mice table, so the units are molarity, and our rows are I, C, and E. We'll enter directly the molarity of the weak acid, 0.0500. Make sure you include all zeros because that will be related to our significant figures later on. H plus and A minus are at 0. The change will be minus X for the HA, plus X for H plus and for A minus. So our E row is 0.0500 minus X for the HA, X for H plus, and X for A minus. When we solve this problem initially, we're going to ignore this change in X, but then we're going to go back and check to make sure that that assumption was valid. We need to write our mass action expression, which is for Ka, since this is a weak acid equilibrium. So our Ka is written by taking the products, H plus times A minus, divided by the reactants, which in this case is just the HA. And we'll plug in all of the values that we have and rearrange to solve for X. We have the value of Ka directly in the problem. We don't need to calculate it. It's 6.3 times 10 to the negative 5 equals H plus, which is X, times A minus, which is X, divided by 0.0500 because we're ignoring that change in X for the moment. We'll cross multiply and we get 6.3 times 10 to the negative 5 times 0.0500 equals X squared. If we take the square root of each side, then we'll end up with X equals something. Taking a look at our sig figs, we have 2 sig figs in Ka, 3 in our molarity. So when we solve for x, we will round that to 2 sig figs. So doing the math, we have the square root of 6.3 times 10 to the negative 5 times 0.0500, and that gives us, rounded to 2 sig figs, 1.8 times 10 to the negative 3. Now we don't know yet if our x is valid, if our assumption was valid, but if it is, then x equals the molarity of the H+. It's a good idea to always take a look back at the mice table to make sure that once we've gotten x, we know what it represents. Before I go any further to calculate the pH, I want to check the assumption. So to check the assumption, I take the value of x I just calculated, 1.8 times 10 to the negative 3. The units are molarity, divided by the initial HA, which was 0.0500. Units are also molarity, so the units will cancel, and when we multiply by 100, we will get a percent. For sig figs, we have 2 sig figs in the numerator, 3 in the denominator. The 100 is exact, and so when we do the calculation, we will end up with 2 sig figs. So doing the math, 1.8 times 10 to the negative 3 divided by 0.0500 times 100 gives us 3.6%. Our threshold, where we're saying x is small enough, is 5%. So as long as this is less than or equal to 5%, then we're good. Our assumption is valid. And in this case, 3.6 is less than 5, so we can keep the work that we've done for x, and we don't have to solve the quadratic equation. But we have one more step to calculate the pH. pH equals negative log of the h, or negative log of 1.8 times 10 to the negative 3. We don't include the units when we're plugging in to the log because you can't take the log of a unit. We do, however, have to be aware of the rules for sig figs for logs and antilogs. So in this case, we have 2 sig figs in our log term, and when we do the math, that's going to give us 2 decimal places in our final result. So taking the negative log of 1.8 times 10 to the negative 3, rounded to 2 decimal places, gives us a pH of 2.74.